So here's our procedure for a bounded feasible set. Again, we'll have to do something slightly different if it's unbounded, but we will deal with that in a moment, maybe tomorrow. So here's our first step is, of course, you need to find your objective function if it's not already given to you. Once you have your objective function, you need to graph the constraints. So you may need to find the constraints if you're reading a problem, and then you need to graph them. Once you've graphed your constraints, you need to find the corner points. So graphing it will give you a guide as to where, not only where the corner points are, but it'll also tell you whether or not your feasible set is bounded anyway. So we definitely need to graph them to indicate whether or not the feasible set is bounded, and then also to see where your corner points should at least approximately be and how many you have. Then we need to find the corner points, and then finally, we just plug the corner points into P. And then we just indicate the min or the max. So we'll plug in all the corner points. We'll plug each corner point into P. I'll get a bunch of numbers. And then to find the min and max, I just look for either the smallest or the biggest of those numbers that I get by plugging all those into P. So that's what we're going to do. So get your vector function, graph the constraints, find the corner points, plug in the corner points, tell me which was the biggest or smallest value you got, depending on what the problem's asking for. Okay, so this is our general procedure. This is just for bounded feasible sets again. We have to do something slightly different if it's unbounded, but I don't want to do that yet. I just want to deal with bounded for a moment. So let's do a couple examples of these with bounded feasible sets. And I'm not going to write these. So, in 7.1, when you guys were setting these up, I was giving you word problems and you had to set everything up from scratch. And I will give you some of those, but not yet. For now, I'm going to give you ones that are basically already set up, and we just need to do this last bit of finding the min max. So here's my first example. I wrote this down, so I got something in particular. Let's find the max. I guess we're doing the min, aren't we? Let's do the min. The minimum of P equals negative x plus 4y. So our objective function is this. I'm just giving it to us. And this is subject to the following constraints. And again, it's a system of inequalities, and it looks like this in this example. Y equals, not equals, sorry. Y, sorry guys, I looked at the wrong part of my notes. The constraints are x plus 2y, less than or equal to 20, negative x plus 2y, less than or equal to 10, and negative x plus 3y is greater than or equal to 5. So this will be our system of inequalities representing our constraints for this example. So I need to find the minimum of this subject to these. Okay. So we'll just go through our procedure. I already gave you the objective function and I already gave you the constraints, so we don't need to find them. So the next step would be to graph this. We need to graph this. So we're going to graph these. And I'll be a little faster about graphing these, maybe. That's what I say anyway. Let's see how this goes. So we'll graph this first guy in red. So that is x plus 2y equals 20. Solve this for y. I think I'm going to get y equals negative 1/2 x plus 10. Okay. So maybe I'm going to count my units by 2s or something. Yeah, do I want to do that? I think I do want to do that. I have a y-intercept of 10. I don't think I want to count up 10 tick marks on my board here. So I'm going to count by 2s. because then I go up to 10 and I'm good. So I have a y-intercept of 10. I'm supposed to be doing this guy in red. Y-intercept of 10, and the slope is negative 1/2. So when I go to the right by 2 tick marks, I go down by 1 tick mark. So right by 2, I go down by 1, and so forth. Okay. Next, I have, oh, and I'm going to shade, so if you were to test a point, I don't know, test the origin, 0, 0, I'll get 0 less than or equal to 20. That's true. So I'm going to shade below the red line. Okay. Next, let's take care of the second one. Is this purple one dying on me already? That's pretty. Okay. Oh. Maybe it's okay. I don't know. They're brand new markers and they're already crapping out on me. Okay, so let's solve negative x plus 2y equals 10 for y. I think I'm going to get y equals positive 1/2 x plus 5. So I'm somewhere, I have a y-intercept of 5. So that's like halfway between 4 and 6. And then my slope is positive 1/2. So when I go to the right by 2, I go up by 1. So it's something like this. Here. This purple line. And if I were to test a point, it would turn out again that I'm going to shade below the purple line. Below. Now it seems to be working better. I don't know what's going on with these markers. So I'm shading below the red line and below the purple line. Again, I could find that by testing point, plug 0, 0 into this. Again, I'll get something that's true. Finally, I'm going to take care of this last one. I don't know, the green work. The green works, I guess. So we'll take care of this one. I get negative x plus 3y equals 5. And I solve this for y. I'm going to get y equals 1/3 x plus 5/3. So I have some fractions, but that's okay. We can deal with these. The y-intercept is 5/3, which is something between 1 and 2. So it's like down here between 0 and 2. It's down here between 1 and 2. Now it's closer to 2 than it is to 0. So it's somewhere in there. And the slope is 1/3. So when I go to the right by 3, I go up by 1. So the right by 3, up by 1, something like this. Okay. And so what it looks like is, oh, and if I ask where I shade for the green line, it turns out I'm going to shade above the green line. So again, take a point not on that line and test it. 0, 0 into here gives me something false. I get 0 greater than or equal to 5. That's false. 0, 0 is underneath the green line, and I got a false statement, so I better shade above the green line. So I'm shading underneath the red and the purple, and I'm shading above the green, which means I'm shading in this big skinny triangle between all three of them. That's where I'm shading. So this is my feasible set, this big skinny triangle. Okay, so how many corner points do I have? Well, the feasible set is a triangle. So I have a corner point down here where the green and the purple intersect. I have a corner point here where the red and the purple intersect, and I have another corner point here where the red and the green intersect. Okay, so now I need to find the coordinates of those corner points. And to do that, again, I'm going to solve the systems of equations that go with these. So if we do this one first, we'll do this one first. Which two equations intersect there? I'm going to maybe erase this part. Give myself some more room to calculate. So here I'm looking for the red, the green and the purple lines intersect at that corner point. So the equations that I had for the green and the purple, let's hope I don't mess this up. It should be the y equals 1/2 x plus 5. That's the purple line. And the green line was y equals 1/3 x plus 5/3. That was the green line. So those intersect here. So this is my system of equations. So now I just need to solve this out. I'm going to substitute this one down here to get the equation 1/2 x plus 5 equals 1/3 x plus 5 over 3. And I'm going to solve this out. So, so I'll multiply both sides by, I have 2 and I have 3 in the denominator. So you guys might have different approaches for doing this. My approach would be multiply by 6, because it'll get rid of the 2 and the 3 at the same time. Multiply both sides by 6. I will get 3x, or 1/2 of 6 is 3, plus 30, or 6 times 5, equals 1/3 of 6 is 2, and 5/3 of 6 is 10. Did I do that right? Yes, about 10. 6 divided by 3 is 2, and then 2 times 5 is 10. So I get 3x plus 30 equals 2x plus 10. Now I'll subtract 2x from both sides, and I'll subtract 30 from both sides. I'm going to get x equals -20. So the x coordinate of this point over here is -20. So what's the y coordinate? Well, I'll plug in -20 into one of these, maybe into this first equation. Y will equal 1/2 of -20 plus 5, which means -10 plus 5, that's -5. So I think -5 is our y coordinate. Okay. So this quarter point is -20, -5. Okay. Next, we find the other two quarter points. And maybe I'll start up here erasing just this much. Let's look at this corner point next. That's the intersection of the red and the purple. The red line had equation, once I solved it out, it was y equals -1/2 x plus 10. And the purple had equation y equals 1/2 x plus 5. So I'm going to solve this system to find this corner point. So again, I'm going to substitute this one into here. Substitute y equals -1/2 x plus 10 down here. So -1/2 x plus 10 equals 1/2 x plus 5. And we're going to solve that out. So I'll multiply both sides by 2. I'll get -x plus 20. The plus, don't want to erase, here we go. Equals x plus 10. Just multiply everything by 2. Get this. Now I'll add x to both sides. And so I'll get 2x. I'll subtract 10 from both sides, and I'll get 10. So it looks like x equals 5. Divide both sides by 2. Get x equals 5. So this x coordinate up here is 5. And now I need to find the y coordinate, so I just plug x equals 5 back in. So I get y equals, I don't know, -1/2 times 5 plus 10. That's -5/2 plus 10. For a common denominator, that's plus 20 over, plus 20 over 2. So I think 15 over 2 is our y coordinate. I'll write these out to a nice summary here in a second, a little more neatly. So my two corner points so far are -20, -5, and 5, 15 over 2.
I have a question.
Yes.
When we find the x there, does it matter which equation we plug it into?
It does not. No.
Okay.
So you could take this x equals 5 and plug it into either equation. It doesn't matter.
All right.
Yep. Any other questions while we're at it? Okay. So yeah, please chime in with questions as we go, if you have any. Let's find this last corner point real quick.